6.1. This is the first one we looked at yesterday. This was just a special case where the coefficient of x was co-prime to the modulus. So when a was co-prime to the modulus, that means a has an inverse. So there's an inverse to a floating around, an inverse to a modulo n. So you simply hit both sides with the inverse of a. Here we've represented it in this form, a to the power of phi of n, where phi is the Euler-Tauschen function minus 1. That's the inverse of a. So you multiply both sides by the inverse of a, and you have the unique solution. The unique congruence class modulo n that solves this congruence. Obviously, there will be an infinite number of integers x which solve it, any integer x which is congruent to this one, modulo n. We also present it that way because this is also like a formula, a computable formula for finding the solution, because we know how to evaluate the Euler-Tauschen phi function. If you can get a prime factorization of the number, you know what the prime factors are, then there's a formula based on the prime factorization which tells you what the Euler-Tauschen function value phi of n. That's just a special case. So then we have to widen it out to the general case of what happens when the GCD of A with n is not 1. So what happens when we allow it to be anything, namely D? So this is the second theorem we looked at yesterday. It says, well, when the greatest common divisor is just something general, D, maybe not 1, then this D, the D and the B, the relationship between those two determines whether solutions exist. And the solutions will exist if D divides into B, okay, or B is divisible by D. So we prove that, okay? This is an if and only if statement, so we prove that in the two directions. But it's just an existence type proof. So it says if D does divide B, then there are solutions. But it doesn't tell you any more than that. It doesn't tell you how many solutions there are, how many congruence classes modulo n solve this. And it doesn't even give you a particular, well, it does give you a particular method to find one, I guess. Because hidden in, if you look in here, the way we show that the solution exists is because we arrive at this integer, rb prime. And a times this integer is congruent to b. So this is a solution. So I guess it's not fair to say it doesn't tell you how to find a solution. It does. B prime just comes from b and d. B prime was b divided by d. Where is that? B prime is b divided by d. And the r, well, the r drops out of applying Euclid's algorithm. So it does give you a method to find one solution, but you have to work through it backwards to get these coefficients r and s in the linear combination of a and n that's equal to their greatest common divisor, d. So it's a bit of a longish calculation method. So we'd like something, we would like something a bit quicker to arrive at solutions, but also we want to know exactly how many solutions there are, okay? Because these coefficients r and s, which give you the linear combination of a and n equals d, they're by no means unique. There's an infinite family of pairs, r and s, which will produce ar plus ns equal to d. Any one of these r's will construct a solution for you to this congruence. But how many different congruence classes modulo n does it produce in this combination rb prime? That's the question we want to get an answer to. Okay, so that's what we're going to look at now. After we've looked at this term, we'll do some examples to apply this. Because if you look at the next page, there's a whole bunch of linear congruences there, various moduli, which we can try applying these techniques to. So this theorem 6.3 is the kind of full story for linear congruences, okay? Full story for linear congruences. So we're looking at a linear congruence ax being congruent to b. From the previous results, in order to have solutions, we need to have that d divides b, where d is the greatest common divisor of the coefficient a of x and the modulus n. Okay? So we know that has to be the case. That has to be the case. And indeed, if you just scroll back, sorry, just before I get into that, when you look at one of these examples here, this example, the 2x being congruent to 3 modulo 4, in the initial example, just by trying all the possibilities, we saw that this had no solutions. You can see how that agrees with theorem 6.2 there, because the greatest common divisor of the coefficient of x in the modulus, greatest common divisor of 2 and 4 is 2, but 2 does not divide 3. Okay, so you can see how that fits with theorem 6.2 as well. Okay, so coming to theorem 6.3 now, this tells us the whole story. So if D does divide B, we know from the previous result that there are solutions. Well, this theorem is saying that there are, in fact, exactly D solutions. So there's D different congruence classes modulo n, which solve this. Okay, so that's good. It tells us how many different solutions there are, and it gives us a recipe for finding them. It says these D solutions, they're represented, the D solutions are D congruence classes modulo n, and they're represented by these representatives. So T plus I times n over D. I is the parameter which goes from 0 to D minus 1, so there's D possibilities for I. And T, what is T? Well, T is the solution of the reduced congruence, where we divide everything, because we know that D divides B, and D is a common divisor of A and N, so all three parts, the A, the B, and the N, they're all divisible by D. So when you divide everything across by D, and there we're employing this kind of situation here, this reduced congruence, this is now an example of a linear congruence where the coefficient of x is co-prime to the modulus, okay, because we've divided out by the greatest common divisor. So it's co-prime, so this one has a unique solution. And so T is the unique solution to this congruence. Okay? So what is there to prove? What is there to prove about that? Well, what is there to prove about that? Well, so first of all, I refer back to theorem 4.4. So that's, or maybe, yeah, theorem 4.4, which is this theorem there. Is it not? Yes, that's our theorem 4.4. So this says, well, you can cancel something from all three parts of the modulus, and it's the two congruences are equivalent. So if you've got a solution x, we think of y as being given, x is the unknown that we're trying to solve for. If we've got a solution x of this, x is the integer x is also a solution of this, and vice versa. If you've got an integer solution x of this, it's also a solution of this. So these two congruences are equivalent when you think about them as statements about the integer x. Okay? So they have exactly the same integer solutions. Now the things we've just listed, those t plus I times n over d, t plus I times n over d, where I varied from 0 to d minus 1, the t was named as a solution of this, okay? So certainly when I equals 0, this number t is certainly a solution of this one, so t is certainly a solution of that original one. Okay, so remember the two are equivalent in terms of, in thinking of them as statements about integers x. Then the other ones, you're just adding on multiples of n over d. So in fact, these numbers, these all belong to the congruence class of t modulo n over d. They're all in the same congruence class modulo n over d. So if t is a solution of this one, then so are all of these integers, t plus I times n over d. Okay? Because t plus n over d is congruent to t modulo n over d. So there are a bunch of different integers which all satisfy this congruent statement. And because this one is equivalent to this one, they all satisfy ax congruent to b. Okay? So certainly then, these d different integers that we've listed, they are indeed solutions to they are indeed integer solutions to our original problem. So we know that much about them. Now the theorem claims something more. The theorem claims that these are all different, these all represent different congruence classes modulo n, and they are a complete set of solutions to AX congruent to B modulo n. There's no other solutions whose congruence class modulo n isn't mentioned here. Okay, so that's two things to prove about. These. Firstly, that these numbers t plus I times n over d, they're all different modulo n. Okay, they're all the same modulo n over d. But we want to show that they're all different modulo n, which is a larger modulus. We'll show they're all different modulo n, and secondly, we'll show any solution of AX congruent to B modulo n, any solution of that is going to be congruent modulo n to one of these. So they're a complete set of solutions. We haven't missed out any solutions of the original congruence. Okay, so that will settle that. That will prove the theorem. That will prove that these d different numbers are a complete set of solutions, and they're all distinct modulo n. Okay. So what we prove first is that they're all distinct modulo n. So I make the claim then in this paragraph, these solutions are all incongruent modulo n. I mean, no two of them are congruent to each other modulo n. So how do we prove that? So this is like a little proof by contradiction. It's like a little proof by contradiction within this. So we suppose that this was not the case. So suppose that they're not all incongruent. So that means you can find a pair of them, t plus r n over d, t plus s n over d. So the r and s are just two values of I. So you've got two of them that happen to be congruent modulo n. Okay? Now that can't happen, but we assume for the moment that it could. So r and s are two example values of I. So r and s lie between 0 and d minus 1 inclusive. Now we can simply subtract the t from both sides. Okay, we want to isolate a statement about the r and the s, prove something about the r and the s. So we can just get rid of the t from both sides just by subtracting t from both sides of the congruence. Still the same modulus. But now apply this theorem 4.3, this first one here. Because we've got a common factor, n over d, there in the two numbers. So we want to cancel that, get rid of it, and just reduce it to a statement about r and s on their own. But in order to do that, this theorem tells us, well, we have to divide the modulus. No, in fact, we're going to be using this one. We have to divide the modulus by that number as well, you see. See, n divided by d is a factor of the modulus n as well. Okay? So we divide all three bits by n over d. So then you're just left with r being congruent to s modulo d. Okay, because when n is divided by n over d, you're just left with d. So then we've got that r is congruent to s modulo d, but r and s both come from the range 0 to d minus 1. And the d integers, 0, 1, 2, 3, up as far as d minus 1, they're all incongruent to each other modulo d. They all represent different congruence classes modulo d. But here we've got two of them, r and s, which seem to be congruent to each other. So the only way that could happen is if actually r and s are the same. Okay, I just run through the statement there about divisibility about d, but that's really just the same thing. Okay? R and s are both coming from this range, 0 to d minus 1. Here we've seemed to say that they're congruent to each other. That can only happen in one way, is if r and s are in fact the same integer. Okay? Because the different integers, 0, 1, 2, 3, up as far as d minus 1, they all represent different congruence classes modulo d. So what we thought, or what we imagined, first of all, might be a pair of two of these. If they're congruent modulo n, in fact, they're not two different ones. We've just written down the same one twice. So that means these d different numbers here, from I equals 0 to d minus 1, they are incongruent to each other modulo n. So they're representing different congruence classes modulo n. So that's good. So to summarize where we're at, we know that these numbers are all solutions to AX congruent to B. And secondly, we know they're all distinct solutions, meaning they all come from different congruence classes modulo n. N is the modulus of the original problem. So the only thing left to remain, the only thing remaining to prove is that those are all of the solutions. We haven't missed out any of the solutions. There aren't any other solutions floating around which might come from a different formula. Okay? So that's the last part. The final part to prove is to show that the solutions in equation 615 are all of the solutions. So, what do we do? Let's suppose there's another solution S. So suppose that S is any solution of this. What we're going to prove is that S is congruent to one of these. Okay? So this solution S, it has to be one of these ones. So that will assure us then that this is the complete set of solutions. Well, if S is a solution, then that means AS is congruent to B. So that also means that AS is congruent to AT. Okay, because T is a solution. This number T, that's when you have I equals 0. T is a solution. So we have AS being congruent to AT. And now we're going to employ this statement here. You've got this common factor of A on both sides. I've renamed my S suddenly to a Y. So could you correct that in your notes? Which one do we mention most? It might be simpler to rename the S to Y straight away up the top. I think we mentioned Y more times down below. So call this S a Y, and call that second S a Y as well. Okay. Sorry about that. So we got AT being congruent to AY. So we want to cancel the A. So we can do that. But we have to divide through by the greatest common divisor of A with N, okay, which is D. Okay, so we're employing this theorem 4.3 here. Okay. So now we know that T is congruent to Y modulo N over D. So Y is a solution of the reduced congruence as well. Okay. So Y is congruent to T modulo N over D, so that means Y must be T plus some multiple of N over D. That's what it means for Y and T to be congruent to each other, modulo N over D. But now this is just some integer Q. But certainly this integer Q will be congruent to one of our i's here, modulo D. Okay? Because our i's go 0, 1, 2, 3, all the way up to D minus 1. So the i's here are a complete set of residues modulo D. So this Q will be congruent to one of these i's, congruent to some I, modulo D. So, hang on. Yeah. So Q is congruent to I modulo D. So then we multiply all parts of that by N over D. Multiply both sides of the congruence and the modulus by N over D. So again, we're using this property where we're going from a left-hand side to the right-hand side. We're multiplying all three parts by some fixed number C. So here, we're multiplying by N over D. So we get that Q times N over D is going to be congruent to I times N over D modulo N. So that means that this Qn over D here, I can replace by In over D modulo N. Okay? So that tells me that this Y solution, which was supposedly another solution of AX congruent to B, it is in fact congruent to T plus I N over D modulo d for some I. Okay, so it is congruent to one of these ones over here. See that d there? Change that to n. That should be n to match this one here. Because we're taking y is equal to t plus qn over d, and we're replacing the qn over d by something, another thing, in over d, which is congruent to modulo n. So this is an n there, that modulus. Sorry, I'll have to go back and I'll correct those and stick the corrected version up on Moodle, send an announcement around. So that completes that last part. Very quickly, we proved first that all these numbers were solutions. Secondly, we proved they're all different solutions, meaning different congruence classes modulo n. And thirdly, the last part was to prove these are all of the solutions. There's no other solutions out there floating around. We proved that because here we gave ourselves a general solution y up here of ax congruent to b, and we ended up concluding that y was congruent to one of these modulo n. So that means that this recipe here is capturing all the solutions. Okay. So this y is not some new solution, it's one that's captured already here. Okay. So okay, any questions or queries about that? So I guess to make it a bit more concrete, we should dive into some of these examples. So basically, we should be able to solve any linear congruence now, okay? Because we've seen the full story about them all. So let's have a look at these two examples, and then we'll take some time to try some of the other exercises there as well. So if we look at example 6.3, so to solve this, we'll need theorem 6.1, 6.2, and 6.3. So the first one is 5x being congruent to 3 modulo 24. So what's going on here? So the first thing to check is we need to obtain the greatest common divisor of the coefficient of x in the modulus. Okay. First of all, we obtain the GCD of 5 and 24. Now, if those numbers are big, you might need to recourse to the Euclid's algorithm, or you might need to factorize them into primes and spot the overlap in the prime factorizations. Or if they're small enough, you can kind of, the answer just pops into your head. Is there any common divisor of 5 and 24? Well, yeah, there is. There's one. Yeah. There's no non-trivial common divisor, but there is a common divisor. Yeah, sorry. But you're right when you say there isn't any common divisor. Apart from one, there's no common divisor. Yeah. So they are co-prime. So that means theorem 6.1 tells us there's a unique solution. So there exists a unique solution. That's theorem 6.1. And it's given by x is congruent to 5 inverse times 3 modulo 24. What is 5 inverse modulo 24? What? 19. Yeah, that's 24 minus 5. Yeah, no, multiplicative inverse. That's its additive inverse. That's the additive inverse. Multiplicative inverse. What number do you multiply by 5 to get something congruent to 1 modulo 24? 5. 5 is its own inverse. So 15 modulo 24. That was pretty good. That was pretty fast. That's certainly faster, I think, than we would have found a 15 by just doing exhaustive search. See, any of these problems, they are only finite. There's only a finite domain from which the solution might come. Because there are only 24 congruence classes modulo 24. So we could just do a kind of mindless search for, try 0, try 1, try 2, try 3. Could just search through all the possibilities. But, that's not very sophisticated. If there is a solution there, you'll find it, but you won't know why you found it or why there was a solution or why there wasn't. So applying the theory here, you see we do quite quickly, even using our slow brains, slow human minds, we can quite quickly arrive at the solution, x congruent 15. Is that right? Is what's 5 times 15 is 75? 75 congruent to 3 modulo 24? Yeah, 3 times 24 is 72. So 75 is congruent to 3 modulo 72. So yeah, it checks out. But what we also are assured of now is that 15 is the only solution modulo 24. There isn't any other solution. Because even if there was another solution, 5 inverse exists, so you can hit both sides with 5 inverse, so the solution has to be congruent to 15 modulo 24. Okay, so there can't be another solution. Is that okay? So let's try the next one. 25x congruent to 15 modulo 120. So now there's like, if you had to search for a solution, you had to search 120 candidates. So we certainly don't want to do that. So we definitely want to apply this. So again, we need to check the GCD of 2, 5, 25, and 120. We need to check that that divides 15. Hope it does. Well, 25 only has 2 factors, only has 1 factor, 5 times 5. And 5 is a factor of 120. So the GCD is 5, isn't it? Has to be 5. 120 isn't a multiple of 25. Does 5 divide 15? Yes, true. So theorem 6.2 tells us there are solutions. Okay. There are solutions. Now, it's not like the previous example. There isn't just a unique solution. You can't multiply both sides by the inverse of 25. Why can't you multiply both sides by the inverse of 25? Surely you could, and then you just x is congruent to 25 inverse times 15. Why can't you do that? Surely I can do that. Sorry? It doesn't have an inverse. There is no 25 inverse. I was about to write it down, and then but yeah, I can't write it down. There is no 25 inverse. So I can't write down 25 and stick an inverse sign on it because it doesn't exist. Good. So just a note, 25 inverse modulo 120 does not exist. So it doesn't exist, you certainly can't use it in your calculations. So we need to go to the method of theorem 6.3. So we apply the method, the formulae of theorem 6.3. So we look at the reduced congruence. What's the reduced congruence? The reduced congruence is where you divide all the way across by this number 5, by the greatest common divisor of 25 and 120. So the reduced congruence is 5x congruent to 3 modulo 24. Thank you. What's the solution of that? I mean, you can't see the solution of that. 15 is the one we did a minute ago. 15. Yeah. So that's our t. That's the unique solution. Well, unique modulo 24. So this is our t. So t equals 15. And there are 5 solutions in total. Remember, the d was 5. That's the d in the language of the theorem. There are 5 solutions in total to 25x congruent to 15 mod 120. And these are represented by t, which is 15, plus I times n over d. So the n over d is 24. And this is the I ranging through 0, 1, 2, 3, and 4. So these numbers, these are congruence classes modulo 120. So these are 15, 39, oh my God, 64, 54, 69, 84, 115, 99, isn't it? 99. So 1, 2, 3, 4. Rain, 0, 1, 2, 3. Ah, jeez. Ah. I was adding on 15 each time. You want to add 24 each time. God, 59. 63, 87, and what's that, 111? Do you add 24 on again? No, if you add 24 on again, you get 135. What is it about 135? It's congruent to 15. It's congruent to that one. So it's already listed. Okay. You can keep on adding 24s onto any of these, but you'll just hit other representatives. So these are our 5 solutions modulo 120. Okay, that's good. Any questions about it? Or why don't you try, we've got 10 minutes or so, why don't you have a look at some of those other examples there? Exercise 6.1. Certainly when the modulus gets large, when the coefficients get large, you're certainly out of a situation where you want to be doing any just kind of trivial exhaustive search through all the possibilities for solutions. So you definitely need these results in order to make sense of some of them.